Hello, everyone. My name is Nikki Andrzejczyk. I work at NAVFAC Exwick in Port Hueneme, California, and I would like to thank you all for attending the Open Environmental Restoration Resource webinar on understanding PFAS leaching. Our speakers today are Charles Schaefer from CDM Smith and Chuck Newell from GSI Environmental. Chuck and Charles will examine the science, challenges, and strategies involved in managing PFAS leaching to groundwater, focusing on the key processes, decision-making frameworks, and current remediation approaches. At the end of the presentation, we will be having a Q&A session, so we highly recommend that you submit your questions throughout the presentation via our chat box. This presentation is being recorded, and the PowerPoint presentation, as well as the recording, will be posted on our public website. Following the webinar, a link will be available to a short survey. Please fill out the survey as it is our main feedback mechanism, and it should take less than 2 minutes to complete. Next slide, please. I want to emphasize the following important disclaimer. This webinar is intended to be informational and does not indicate endorsement of a particular product or technology by the Department of Defense or NAVFAC Exwick. Although every attempt is made to provide the most accurate information, there is no guarantee that any technology or product will be suitable for your site. Next slide. Before our speakers begin the presentation, I would like to invite Nate DeLong from NAVFAC headquarters to say a few words about the OER2 webinars.
Thank you, Nikki. Hi, everyone. My name is Nathan DeLong, Acting IR Program Manager at NAVFAC headquarters. We appreciate your participation in the Open Environmental Restoration Resource, or as we like to call it, the OER2 webinar series. We have been providing this OER2 webinar series since about 2014, and we look forward to providing another informative topic for you all today. This webinar series is typically for RPMs, RTMs, contractors, and others who support the Department of Navy Environmental Restoration Program. Our goal with this webinar series is to really provide a venue for two-way communication on issues affecting the Navy environmental restoration community by both reaching out to and obtaining feedback from you, the community members. The emphasis of the webinar series is to share information openly and to promote innovations among the environmental community. This is done via Navy policies, guidance, tools, technologies, practices, initiatives, and/or lessons learned. OER2 webinars are typically offered quarterly and are announced via the Environmental Restoration T2 emails. We'd also like to remind you that feedback from our environmental community members is key to sustaining this series. So please, as Nikki said, feel free to let us know how we've done on this webinar and then recommend future potential topics or to volunteer as a presenter. Any potential topics submitted should be relevant to the Environmental Restoration Program and should not contain marketing materials. If your topic is selected, you will work with a Navy champion and possibly a co-presenter. As Nikki mentioned, today's webinar is entitled Understanding PFAS Leaching, Key Processes, Decision Frameworks, and Management Strategies. There's a lot of really good information to get to within this topic and this presentation, so I don't want to take up too much more time. So with that, I'll hand it over to today's presenters, Dr. Charles Schaefer and Dr. Charles Newell, to get us started.
Okay, well, I guess we're on slide 4, but let's go ahead and go to slide 5. This is Chuck Newell speaking. And then today we've got this roadmap. We've got these 7 or 8 different topics that Charles and I are going to go through and almost sort of try to have a conversation on here. But let's just go through what the 8 different sections are going to be. Introduction. Charles and I are going to look at 3 different graphics and sort of go back and forth on what they mean to us about PFAS leaching. Number 2, how does PFAS leaching work? The key processes. If you're into chemistry, this is going to be really good for you. Number 3 is the one key decision-making framework, and that's PFAS mass discharge. And if you're a water person, hydrogeologist, looking at any sort of flow of water through the subsurface, this is going to be of interest to you. How to characterize PFAS leaching sources. This is if you're a person that likes to be outside and collecting the data from our sites. Number 5, PFAS leaching computer models. If you're more of a person who likes to stay inside, your cube is close to the kitchen, whatever, then this is how you can model these sites to help make decisions. And finally, 6, key decisions for managing this PFAS leaching, wrap up in a Q&A. Okay, well, let's go to slide 6, and here are 3 graphics and that we're going to talk about. But if you see a slide that looks like this, that means we're going on to another section and the little divider in here. So now let's go on to slide 7, and we're going to talk about PFAS classes and nomenclature, our first of 3 graphics. Now, Charles, this came to you, and when I saw this, I noticed on, there are these 3 different boxes, and on the far right, there's polymers. And in some ways, we don't have to, worry about that. This stuff like Teflon, so environmentally not important. But the stuff in that left box and that middle box, these are the drivers for our business. And Charles, so what do you see or think about when you see this figure?
Yeah, Chuck. So when I look at that box on the left, I think of the compounds that most of us think about, the ones that are regulated. PFOA is a perfluorinated carboxylate. That falls in that category, and so does PFOS, which is a perfluorinated sulfonate. But as many of you may know, there are larger and shorter chain compounds within these classes. These are the compounds that are really the focus of most of the current regulations right now. These are very recalcitrant to any sort of naturally occurring transformation. But then we have this box of compounds in the middle there that are termed precursors, and you can see that they have the similar tails there, but they have these different head groups. And these head groups are more susceptible to transformation, naturally occurring abiotic processes, naturally occurring biotic processes, and they can be present in a lot of these AFFF impacted sites and then form some of the compounds that are in that leftmost box. Another thing that's interesting is that there are some different charges on some of these precursors. So the compounds in the left box tend to be anionic. There are some in that middle box anionic precursors, but some are cationic and some are zwitterionic and have some negatives and positive charges, and that can really impact how the contaminants partition, especially the soil.
Yeah, and just one last thing is that our other contaminants that we're used to, TCE, benzene, all these guys, this biotransformation is something that we like. It destroys those contaminants. But here it actually hurts you because transformation of these precursors to the PFAS often means the generation of a regulated stuff. Right, Charles?
That's absolutely right, Chuck. Great point, and it's certainly something that we need to think about, not only as we are monitoring these sites, but if we sort of try to implement any sort of remedy for these sites.
Okay, let's go to slide 8. Now here's another image. This is from Dr. Bogo at University of Arizona, one of the world's leading researchers in this whole leaching aspect. He's more focused on modeling, but certainly with some lab studies. But Charles, when you see this figure, what do you see? What do you think about?
Man, one of the things that strikes out to me the most, Chuck, is this accumulation at the air-water interface, and that's kind of something we're not used to thinking about, right? When we think about chlorinated solvents or hydrocarbons, but PFAS can absorb at the air-water interface, and depending on how much water and air you have in your system, that could change with moisture content. What do you see?
And so on this. Yeah, well, I see there's 3 different scales here. On the left, you got the figure. There's one fire going on, representing one of these fire training sites. Then you sort of tunnel in, and you're at the pore scale, and you can actually see these little things sticking out of that. In the vadose zone, the water forms these films around the soil particles, and you can see the PFAS there. And then he says, well, this is one of our big targets is that PFOS, and shows the actual chemical itself. Well, let's go to the next graphic, slide 9. And in a lot of these graphics, we were asked by some of the Navy experts, put in some of the structures of these things. We've done that. And on slide 9, the big block figure, again, from Dr. Bogo's group at University of Arizona. This is a sort of a different view. But what I noticed is, of course, they've sort of expanded their use of the fires. There's 5 of them there. But then, Charles, what's happening in the subsurface in this figure?
Yeah, Chuck. Well, we always like to really simplify things and just kind of draw a straight line or a straight arrow down. But in many cases, that's not how things migrate in the unsaturated zone. You may have some very complex flow paths. You may have some preferential pathways and bypassing and things like that. So some of these overly simplified assumptions that we like to make may not always be appropriate for some geologies.
Yeah, and I see this figure. There's this term we use for matrix diffusion called the revenge of the geologists. And so just this idea that subsurface, it is very complex, and you can get very different behaviors if you consider some of these heterogeneity, factors that are going on in there. Well, Charles, let's go to slide 10. And how about the key questions that need to be answered?
Yeah, so we've drawn a couple of these conceptual figures to think about, but what are some of the things we really need to try to answer at these sites? So the first one is, how does PFAS go from soil down to groundwater? What are some of these controlling mechanisms, and which ones might be real critical to try to understand? What parameters do you need to measure to understand PFAS leaching? What sort of monitoring tools or tests should you be considering? And then once you collect some of this leaching data in whatever form it is, how should you evaluate those data? What does it mean? What do you do with it once you collect it? And then just a couple of the bottom line questions is PFAS leaching at my site, is it causing a groundwater problem, or is it just staying in shallow soil? And if it is causing a problem, how do you predict or forecast future behavior? Is the worst over? Is it going to be around for a few more years or a few more decades? So these are some of the things that I think we need to try to answer, and hopefully we'll touch on some of these in today's talk. Let's go to slide number 11. And Chuck, why don't you talk about some of the key decisions that often have to be made as we try to manage some of this PFAS leaching?
Sure. So one of the key things is, how do you get this mass discharge? This is going to be one of our key metrics that we're going to talk about. Grams per year that's leaving the vadose and going into groundwater. It's pore water concentration times recharge times area. So we're going to tell you how to get those numbers. Number two, how do you determine PFAS pore water concentrations in leaching? And here we've got one of the world's experts on these suction lysimeters. And this is sort of a new gizmo for us who are used to working in TCE and the hydrocarbon world. He's going to tell you all about those. Then you're going to need a recharge rate. How many inches per year this precipitation is actually making its way down to groundwater? And I've got some stuff about that in terms of multiple methods for simple, complex, and in-between sites. We'll talk about the dilution factor. Is this unsaturated leaching impacting the dissolved water plume? And then, do you need to construct a numerical model of all these sites? Is that something, or is there other ways to sort of do this prediction that Charles talked about? And what models are available if we did want to use this? So that's some of the key decisions, and of course we're going to flesh those out. But we're going to go to the chemistry, slide 12, PFAS leaching, and sort of these processes that are going on. And with this, we'll drift into slide 13. And I'm going to start on the right-hand side of this. And Charles did say that we're looking at some of our key PFAS, these key PFAAs, things like PFOS and PFOA. They have a negative charge on them. They're anions. And so you can have some of this, then these don't typically have enough of a charge to stick to soil. So we're saying like these PFAs are anions. They don't really stick to soil, so they just move. And you think like a chloride plume, it's negative charge. It's the same sort of thing. But some of these precursors are cations. They have a positive charge. And at one of our research sites that we looked at, there was these positively charged cations, and those guys really like to stick around the soil. They didn't move very much, very short plumes compared to the anions. Now, on the left-hand side, here's this air-water partitioning that Charles talked about. You want to go through that panel and then drift into slide 14? Mm-hmm.
Yeah, so the basic chemistry of it is these tails, these perfluorinated tails that are associated with PFAS are very hydrophobic. They don't want to stay in the water, so they will align at the air-water interface. So what unsaturated soils can have a very high air-water interfacial area, and PFAS, that's another accumulation mechanism, just like the soil. What's interesting with this process, though, is that the air-water interfacial area can change, right? When things are very dry, you can have a high air-water interfacial area and a lot of accumulation there. And when things are very wet, that tends to decrease. The other notable thing is that for very long chain compounds like PFOS, they have this very hydrophobic tail. You'll get a lot more accumulation of PFOS at the air-water interface than you will of a shorter chain compound like PFBS or PFPES.
Okay, we're going to move on to 14. Are we already there?
Yeah, let's move on to 14. And we were talking about the importance of the air-water interface. What I have shown here are some results that came out of Mark Brousseau's group, and these are just some bench scale column experiments with a sandy soil, and he's looking at PFOA transport through these columns. And on the left in the blue, you see the migration under saturated conditions. There's no air-water interface, but then he dries the column out a little bit, so you have some air-water interface, and you can see that the rate of elution of PFOA through those columns takes longer when you have more air-water interface. And that's because PFAS is accumulating at the air-water interface. And this was just a very nice proof of concept type of experiment to show that this air-water this PFAS accumulation at the air-water interface really does have an impact on PFAS migration, and probably something we need to account for as we're considering PFAS leaching in situ. So we can move to slide 15, and Chuck, why don't you start talking a little bit about PFAS mass discharge?
Okay, and again, this is grams per year. Let's float over to 16, and this is a quote from a paper that I wrote along with Hunter Anderson who was with the Air Force at that time, now with the CERTA PSTCP, and several of my GSI colleagues. But we talked about how this soil to groundwater contaminant mass discharge, it's the authoritative metric defining source strength for these PFAS sites. And it integrates three things: this concentration, the amount of water flowing through the source, and the size of the source. And to help explain that, and to go into a little bit of the terminology, on slide 17, we have the slide that was part of an ITRC mass flux, mass discharge training that I think I did like 12 times online. And I would always show this graph. But on the left-hand side is this, in the groundwater, this is a vertical plane. It's a curtain that water is flowing through. And if you do these measurements of how much water is flowing through different parts of this, and more importantly, what the concentration is in this vertical transect, you get a mass flux, mass per area per time. And sometimes we use the word mass flux to mean mass discharge, but the ITRC said, no, we should be very specific, much more specific about our nomenclature. And that mass flux is just mass per area per time. Now, in the vadose zone for leaching, we're actually talking about a horizontal control plane that we're trying to figure out what's passing downwards towards groundwater. But then if you have this mass per area per time, and then you integrate it, and regarding how much area is in there, you sort of add all this stuff up, then you get this mass discharge, and that's mass per time, like grams per year that's going through this. And then for the graphic anyway, I decided, well, if we're going to integrate, I know that Isaac Newton was somebody who really was one of the two people who invented calculus. And so he's actually looking at that mass flux transect on the left. He says that plume has the mass discharge of 1.5 grams per year. And so with this, just another side note, is that while I was looking for a picture of him, I discovered two amazing things about the guy. And the first was that he didn't call calculus. He called it the method of fluxions. So even back then, he was thinking about us doing mass flux for our environmental work. So that was the first thing. And then Charles, the second amazing thing that I discovered when I was reading through or looking at this picture?
No, Chuck, but I'd love to hear you tell us.
Well, and maybe it's particularly pertinent to you and me, but man, the guy had really great hair, right? Okay.
Can't argue with that.
18. Exactly. Let's go to 18, and now we're going to talk about looking at a vertical cross section. Okay, so this is going down into the subsurface. You can see the water table in here, and we have these three elements that make mass discharge. That the flux is going to be the recharge times the leachate concentration. Then you add the area in there, and you're going to get this mass discharge. But we're going to start first with pore water concentration, the first of these three different elements to do these calculations. And let's go to option one. How do you get this pore water concentration in nanogram per liter? Let's go to slide 19.
Yeah, Chuck.
Charles,
so,
you're going to take this one, right?
Yeah. What you ideally want to do is be able to measure a soil concentration, a soil sample in the field, and be able to convert that and say, hey, this is what the PFAS aqueous or pore water aqueous concentration is going to be. And what you try to do is look at the partitioning among phases. What makes it a little tricky for PFAS are a couple things, and perhaps the most important is you have PFAS accumulation at the air-water interface, right? And how do you get a prediction of that? And that's something we're going to talk about. The other is that some of the partitioning between the aqueous and the solid phase is a little bit unexpected, and some simple KD models may not apply. So there's a lot more complexity here than maybe what some simple, more simple, more basic fundamental models don't show. So let's go to the next slide, slide number 20. So we're talking about trying to get a prediction of the PFAS concentrations in this unsaturated soil pore water. And why do we even want to know that? Well, that's because that can relate to the concentration of PFAS in the groundwater. In fact, the EPA traditionally has essentially developed its soil cleanup criteria based on that type of relationship. And basically what's used there is a nice dilution factor, right? There's the concentration of PFAS in the pore water, then there's some dilution factor, and that's what essentially the concentration would be in the groundwater. Now, that figuring out what that dilution factor is, there's a lot of empirical or semi-empirical models for that. It'll depend on things like the groundwater flow velocity. It'll depend on things like the source area length parallel to groundwater flow, some sort of mixing factor or mixing thickness in the water, and another big factor is the infiltration rate, which is tied into the recharge rate, which Chuck will be talking about a lot more later. But let's dive a little bit more into this relationship and how we can go from soil concentrations to predicting that pore water concentration. So moving on to slide 21. You see a couple of equations there, and what I have shown as that top equation is really the traditional approach, and something the EPA as well as other regulators have used for helping to establish soil cleanup criteria. So you have this CT, this total concentration. This is what you would measure in a soil sample, and you can basically calculate your pore water concentration essentially if you know your KD. So it assumes a linear partitioning model, and this works reasonably well for a lot of classes of compounds, but for PFAS it's really more complex. So you look to that second equation, and again, how do we derive a pore water concentration from the concentration we measure in the soil? Well, let's look at that second term circled on the right. You have this air-water interfacial accumulation term, right? And that depends on two things: how much air-water interface you have, and the affinity of a specific PFAS for that air-water interface. The other term I have circled is that KD, and I've alluded to this before, and we'll dive into this in a couple of slides. PFAS may have a much more complex desorption phase partitioning model than this. So this type of simple model might not be appropriate for PFAS, and you may end up coming up with too conservative of a soil cleanup criteria if all these terms aren't properly accounted for. So let's kind of dive a little deeper into this and go to slide number 22. And on this slide, we have some data from a AFFF source area, where we have some data from some lysimeters where we sampled pore water in the field and measured PFAS concentrations in those pore waters. Those are the solid blue bars. And then we also grabbed a soil sample from that depth and looked at took it back to the lab and just looked at the PFAS concentrations in a soil water slurry. Please note that this is plotted on a logarithmic scale. Now, what you would expect is to see much lower concentrations of the PFAS in the slurry than you did in the pore water, because you have such a high, we had about a 3-to-1 liquid to solid ratio, so you're diluting the PFAS out. And that's essentially what you see. You see the solid blue bars extend the hatch bars for most compounds. But for some of the most hydrophobic and surface active compounds, so compounds that accumulate at the air-water interface the most, you actually see the opposite. You actually see for PFOS and A2FTS, you actually see about 10 times higher concentrations of these PFAS in the slurry than what you saw in the actual pore water. And why is this? Is because in the field, you had a lot of PFAS accumulated at the air-water interface. When you introduce them into a slurry and you're completely saturated, you remove that air-water interface, and now all the PFAS go into solution. So why is this important?
Charles?
Why am I? Yeah.
Oh, just a quick question is that you got the structures on the right, and the top one is PFOS, our good friend, but the bottom one, that's one of these precursors, right? Mm-hmm.
Exactly. That A2FTS is actually a precursor that can transform into perfluorinated compounds. Absolutely right, Chuck. Mm-hmm. So what we see here is, this is a great example that really kind of proves the importance of these air-water interfaces in situ, but it also tells us how misleading some of these batch tests can be if we're using that to tell us what our PFAS concentrations actually would be in pore water. So you really need to account for that air-water interface. Let's go to the next slide here. And here we have some batch testing to look at PFAS absorption to the soil and understanding this behavior here. One thing we found is we did a kinetic test. So we had these slurries and we're looking for PFAS in the aqueous phase over about a 2 or 2.5 week period, and we found that the concentration slowly increased. So there are some kinetic limitations, some rate limitations as to how quickly PFAS can come off the soil. We also did some isotherm work. So we do some sequential dilution. So you see that figure to the right. So you're kind of moving right to left. So you see a linear desorption behavior, but it doesn't go through 0, 0. In this case, for PFOS, there's a large fraction of PFOS that is essentially resistant to leaching, resistant to desorption, and doesn't readily come off the soil. Altogether, this tells us that some of these very simple leaching tests or desorption leaching models that rely on a simple KD model are really not going to be appropriate. So this is a lot of technical detail, but if you go to slide 24, maybe Chuck, you can kind of get us to where the rubber meets the road here, and what do some of these processes, the absorption of the air-water interface and some of this desorption behavior, what does that mean for actually developing appropriate soil cleanup criteria?
Well, this is a paper from Mark Brousseau, University of Arizona, and he's thinking about these dilution attenuation soil screening levels. We've done this for other contaminants, and he's just trying to say that for these different PFAS that are affected by this air-water partitioning, this is a big deal. So he's running the model 2 ways, and he's putting all this data in about the soil type and the water content and things of this nature, and then he's running just the standard model, which doesn't have the air-water partitioning in it, and then you come up with this safe level of what the PFOS could be in the water, and they say, well, to protect it to this particular criteria, their target concentration, which I think is 100 nanograms per liter on this one, they say it has to be under 4 micrograms per kilogram. But they say, no, you're missing this process. And so, Charles, under the revised model, what happens?
Under the revised model, when you account for PFAS accumulation at the air-water interface and what that means in terms of mass balance, now you have a revised soil cleanup level that's almost 20 times greater than what it was under the standard model. And if you take that a step further, Chuck, and you also account for this desorption behavior and this fraction that doesn't come off, doesn't well desorb from the soil, you're almost 2 orders of magnitude higher with a 290 microgram per kilogram cleanup level. So obviously these fundamental processes, these desorption at the air-water interface, this resistance to desorption can have an extremely important impact on leaching and ultimately what soil screening or cleanup levels you need to obtain at your site.
Okay, well, let's go to slide 25. So those are some options about using soil data, nanogram per kilogram type numbers to try to get information on how it might impact the groundwater. Now, here's another option. We just take some of the soil out there, we send it to the lab, we tell them to do this synthetic precipitation leaching test, and we can get some numbers there on what is that nanogram per liter concentration of the water coming off this. And there's just different perspectives on this. So we're going to just tell you 3 of them. And one of them is from Rivero, 2023 Battelle presentation. I was there. And they said, we're going through this and we think, yes, this is a good way to do this. It's conservative, but it can get you in the ballpark. And so that's one perspective about using these leaching tests. But another perspective is on the right-hand side. And this is coming in and saying, well, no, this is really unrealistic. These liquid to solid ratios far exceed the natural pore volumes. You eliminate these key retention mechanisms, air water partitioning, that soil integrity can be disrupted. Don't go down that road. So that was perspective 2. And then perspective 3 is that the DoD CERTIP ESTT program has invested quite a bit of research money on saying, hey, can we use these and how would we use these? And maybe we should use the EPA's LEAF methods, this leaching environmental assessment framework. So a lot of these methods are being adapted to try to use for PFAS. So let's go to next slide 26, and then this is really where I think that one key part of our presentation is using porous cup lysimeters for PFAS leaching. And this is a paper from Costanza 2025. From the EPA, and they talk about application of these things. They're widely used, and then you actually basically suck out with a vacuum that water that's around those sand grains, and then you just take that to the lab. So you don't have to do any partitioning equations. This is sort of the advantage. It's a direct measurement of that pore water concentration, and it's not that hard to do. But there may be some limitations here. There may be some interactions with the lysimeter materials. The spatial and temporal variability, you got to be careful about that. And then we got these pictures. But Charles, you want to just describe the pictures real quick, and you're going to show a little bit more about that in the next slide too, right?
Yeah, absolutely, and they certainly, raise some questions and concerns here, and I think we can talk about them a little bit. And I think some of those concerns we can allay a little bit. But these figures show how the PFAS pore water is pulled in via vacuum suction and allows you to collect samples especially in sandier type soils where you have decent permeability. But we've done, as you pointed out, Chuck, a lot of work, and I know we have a project or 2 together that we're working on this. So let's move to slide 27, and
a quick question,
we can talk a little bit about. Yeah.
Just roughly, how many sites have you applied these suction lysimeters to for PFAS?
That's an excellent question, Chuck. Probably somewhere, at least 15.
Got it. Okay.
15 or so
some
slides.
Of your learnings on slide.
Right.
With your learnings are on slide 27, right? Mm-hmm.
That's right. So some of the things that that we found is it's not a bad idea to kind of pre-rinse your your lysimeter equipment with PFAS-free water and methanol. Maybe this is not so important if you're in an AFFF source area, but if you're looking more for a background location or a much less impacted location, this might be something that's worth doing. When we install these lysimeters, we really try to limit the annular space, so there's not a lot of just some of this silica flour and the water that's associated with that. We really try to minimize that volume. One thing that was, I think, brought up in that Costanza paper and something that we've looked at is there's concern about how PFAS might absorb to the lysimeter or the silica flour materials. We have looked at this, at least for PFAS as hydrophobic as PFOS. We've been able to show that absorption to the silica flour was negligible, and essentially to the lysimeter itself, especially if we do a small pre-purge. So our data really show that this is not a big concern. Now, if you go something much more hydrophobic than PFOS, then maybe that would need to be reevaluated a bit. We like to add a bromide tracer to our silica flour, and that's just to ensure that once we like to do an initial pre-purge of the sample to get some of that non-native water out of the silica flour pack, which is kind of poured in there like a thick pancake batter mix. But to make sure we're not getting a dilution effect, we like to put, like I said, a bromide tracer in there, and that has served us pretty well, especially to ensure when we're getting real soil pore water. So let's go to slide 28. So in addition to using lysimeters, which is a great in situ technique, we've also developed a bench scale method of collecting pore water. And this can be really useful at sites where maybe it's very deep, or maybe it's too dry, or we just can't collect a sample in the field. We essentially use these what I term micro lysimeters. They're just a miniature version of what we use in the field, and we can collect impact soil cores or just collect soil and repack them and essentially extract a pore water sample in the lab. Again, this can be a very useful tool for validating what we're measuring in the field to show that we are collecting a representative sample, and it also address concerns with preferential flow and things like that. So moving to the next slide, slide 29, we went out to several sites and basically compared the PFAS concentrations we measured in situ in the field in pore water. That's the blue bars here, and the red hatch bars are what we measured in the pore water in the soil sample we came back and using those micro lysimeters. And again, what we found for almost every case was we had pretty reasonable agreement between the two, at least within kind of the margin of error. And that tells us, I think, for a lot of sites that we are collecting a very representative sample when we're out in the field with these lysimeters. But let's go to slide 30. Chuck, as you know, nothing ever works perfectly, right? So here's a case where we did that same test, and here's the same type of data, but now we're measuring concentrations that are 10 to 100 times higher in that micro lysimeter back in the lab. So we were really scratching our heads on this one. This site was a little bit unique in that the soil had been removed, excavated, thermally treated a couple of decades ago to deal with some hydrocarbons, and then put back in. Also, in the lower right-hand corner there, there's some GPR, ground penetrating radar data, and in the area where we put our lysimeters, you can see all these anomalies. So something may be a little bit funny here with the flow. Maybe there's some very structured or short circuiting going on here. Maybe that explains why we see the difference. But I think it certainly points to two important practical things. One is that I think we need to understand our geology when we do this, and then second, I think it points to the value of not just having the field lysimeter data, but some other tests other tests as well. And just looking at one other slide as we move to slide 31 here. Here is some lysimeter data in an AFFF source area at a former Air Force facility, and we took 3 rounds of both groundwater and pore water data, and the soil had increasing saturation or increasing wetness. The first round only 28% saturated, then 63, then 100. And as the water table came up a little bit. And we really, if you look at the bottom row for the 4 different PFAS that we're evaluating, you really don't see much of a trend. Now, if you start looking in the pore water, in the sandy zones, you see a little bit of a trend for PFOS, and that's our most surface active compound. So you would expect as it gets wetter and those air-water interfaces collapse, more PFAS is put in the water. But look at the clay zones, these very fine zones, and very fine soils tend to have higher air-water interfacial areas, so it magnifies this effect. Now you see even the less surface active, the less hydrophobic compounds, you can see this trend. So what's the big takeaway here is that when we're evaluating PFAS pore water concentrations, we have to pay attention to both the geology as well as the moisture content or the level of saturation. It may not be static in time, and this may not be the same across your site depending on the geology. So Chuck, why don't we kind of transition from this into a little bit of mass discharge on slide 32.
Okay, so now the mass discharge, you need these 3 things, and we've talked about the pore water concentration, the yellow box. Now we're going to talk about the blue box, the recharge rate. And both Charles and I originally were chemical engineers, so we love this chemistry stuff, this concentration stuff. But my master's degree, I spent some time hanging off bridges, collecting, stream samples and measuring flows and things like that. So I'm going to put on our hydrology hat and describe how do you get this recharge rate, the amount of water that's reaching groundwater. So let's go to slide 33. This is from an amazing book by Richard Healy, all about recharge. Everything you know, has chapters from Bridget Scanlon from University of Texas. But this is some of the nomenclature they use, and sort of like mass flux and mass discharge, some of the terms are used in different ways or interchangeably, but they're very specific as you have precipitation on the top right. The amount of precipitation that enters the subsurface is infiltration, and in their definition, what reaches groundwater is recharge. And so we can see here that on the left end, there's some different things that happen that make the difference on how much infiltrates versus how much recharge. There's evapotranspiration where water is sucked out of the top part, the shallow soils, and you can actually have the pore water moving up. And so there's a dividing line between where pore water is moving up during dry periods and moving down during wet periods. And that's called the zero flux plane that you can see here. Look at these arrows. So we're really trying to figure out that diffuse recharge on the bottom, because on the right, you see this stream that has focused recharge. We don't have many of our AFFF sites in a stream, which is fortunate. We're focusing on diffuse recharge. And now let's go to slide 34. And this is just this access to tools. This Vadozone paper that I mentioned before, you can find it, PFAS, Vadozone recharge, just put that into the Google. It's open access, so it's free, but it says here are 3 tiers of all these different methods. There are 4 tier 1 methods, 6 tier 2 methods, 5 tier 3 methods, where tier 1 is for simple sites, tier 3 are for more detailed ones, and just in terms of level efforts are very different. I'll give you an example of one of these 4 tier 1s and then talk about a little of the tier 2s. But let's go to the next page, and that's slide 35. And this is just this beautiful map by this USGS researcher, Meredith Reitz, 2017. And then here is this map of the USA, sea to shining sea. And then this has got on 800-meter pixels, and you can get the shape files to look at your site, see your backyard or to see your site, and it will give you an estimate on the recharge going from 0 to really high values. And what we're looking at is, you can see, Charles, where you live in New Jersey, right? this says, or Meredith says, your recharge is about 10 inches per year. Does that make sense to you? What soil do you have in your backyard?
Yeah, that does make sense, Chuck, considering the amount of rainfall we get, and generally some sandy soils in South Jersey.
Okay, and then here I am in Houston, Texas, and we actually, I think, get more rain than you, but only 0.4 inches a year. And why is that? Because we're on like 10 miles of this thick gumbo clay that just really, it's not 10 miles, but just that surface runoff, it just comes off. So let's go to slide 36. And now here we've got this tier 2 and tier 3 methods. And in the paper, there are these little cartoons, and looking at that, there's soil moisture methods. If you can measure this vertical distribution of the soil moisture, you can get a recharge estimate. And you can see on the top left, there's like a little cactus, and then there's a tree, and then that depends if it's better in arid or better in humid zones. And so, for example, let's look down below. There's this method called the WTF method. I know what you're thinking. Yes, that stands for water table fluctuation. But you can, if you have, say, real-time continuous information on the groundwater level, you can apply this method. And wherever there's a storm that comes up, you can see that increase, the rise in that water level, and do a couple of calculations and figure out how much of that recharge is. Other methods are unsaturated zone tracer, like this chloride, or some of the bomb isotopes, meteoric chloride, temperature methods, and so all of these are in that paper. So let's go to 37 and sort of wrapping up the mass discharge part. This is still early in the game. There's this tsunami of RI studies that are coming out, but this is very preliminary. And here's a graph of these 5 sites, and we're looking at these different elements. And what's the key takeaway from this data of mass discharge, Charles?
Well, I think one of the key takeaways, Chuck, is I think there's been an assumption that, hey, it's always these unsaturated soils, these screaming high concentrations, they must be the cause of sustaining these plumes. And if you look at your mass discharges in the data here, we see that's not really the case. Typically we're under 20%, and really most of these sites we have data for, the amount of mass coming from that mass discharge from the unsaturated zone is really less than 10% of what's going through the saturated zone. So what do you think the implications of this are, Chuck?
Well, this is still early. This could change. It's very site specific, but it almost suggests that these sources are either maybe something in the capillary fringe, or maybe it's this matrix diffusion, which you're going to study for one of our projects. But it says maybe you don't spend all your remediation money removing these soils if they're only contributing a small fraction to the groundwater mass flux. Okay, well, let's keep going. And then we've got slide 38. We're going to do this obtain the right information. Charles, I think we're running a little long, so maybe we're going to upbeat our tempo a bit. But why don't you go to slide 39 and talk about key data requirements?
Yeah, so I think we can never forget about the geology, understanding the lithology, things like grain size, organic carbon content. These are things that are needed for understanding some of this PFAS phase distribution. Some of the soil investigations we've done, we like to homogenize in 1 foot intervals, at least through the first 5 feet or so, and then maybe larger intervals if we need to go further than that. But again, you really need to understand the geology, and you may need to deviate from this if you want to consider some low permeability zones. I think a lot of cases you can start your initial focus on what the hot spots are. Get some data there, and then kind of start to step out and look at on your perimeter. Let's go to slide number 40. We can talk a little bit about lysimeter installation, and how I like to do these sites. I like to go out and get some soil data first. I like the soil data to kind of guide where I put, at least in large part, where I put lysimeters. And typically we have a lot more soil data, or at least soil locations, than we do lysimeter locations. The lysimeter gives us great information not only on PFAS concentration, but also the PFAS composition. You know, again, when we install these lysimeters, I think we should be cognizant of the geology and any stratigraphy that's there. When I do install lysimeters, it's useful a lot of times to get an extra soil sample right within the interval of the lysimeter porous cup. That way you can have a direct relationship between the pore water that you measure and the soil concentrations. Typically, we like to put lysimeters a foot or two above the seasonal high water table, but this is not a hard and fast rule, right? I think we have to consider the PFAS concentrations or the PFAS soil profile, the moisture, the recharge, the geology, things like what's at the surface, and also considering multi-depth lysimeters. And the next slide, I think Chuck might be able to speak a little bit more to that. The other thing that's probably, I think, still a bit of an area where we're learning is understanding background. How far out from the expected source area should we look, and really what is the background mass discharge. But moving to slide 41, we have some soil data, and maybe Chuck, you can talk about this and how this might, understanding these soil concentration profiles might determine where we put our lysimeters in.
This is your data. It's so cool. You have a humid site where it rains a lot on the right, semi-arid, not as much rain. The y-axis is depth in meters below ground surface, somewhere between 2 and 2.5. And then here are the concentrations for 3 different PFAS. We have PFOS on the top. It's one of these big dogs. It's 8-chain. On the bottom is PFBS, 4 carbons on those tails, and PFHXS in the middle. And if you look at this stuff, you can sort of see on the right-hand side, well, those concentrations for all of those guys are sort of distributed through the site, maybe a little less on the top. But if you go to that semi-arid site, man, all that PFOS is just sticking to the top. And that's because these long-chain PFAS are more sticky when it comes to air-water interface, sort of that sorption, and because you have a lot more of this evapotranspiration and this upward sort of movement of pore water whenever it dries out. Anything you want to add to that, Charles?
Well, just, what you see in soil concentrations might determine where you want to put your lysimeters, and maybe that would determine whether you want to use multi-level lysimeters. It's just another factor, and why it's a good idea to basically get these soil data first before you install your lysimeters, or at least that's what we have found has been beneficial to us at these sites. So let's move to slide 42. Slide number 42. We'll talk a little bit about some of our, how we employ lysimeter sampling. We like to generally sample our lysimeters, during or shortly after a rain event that not only captures, a high recharge, but also it gives us a better chance of actually getting pore water. We do like to monitor the water table elevation as when we have lysimeters out in the field. That can not only be useful for some of the recharge methods that Chuck talked about, but it's also a good way to make sure that our lysimeters are still actually above the water table. An example sampling program might be to do 4 rounds of sampling after an initial purge round, and I think it's really important to try to look at temporal differences and things related to precipitation events. Regarding rainfall events, I think it's useful maybe to get samples after maybe a mild or a moderate rainfall event, as well as some higher storm events. One big question is what minimum pore water sample do you need? I think that can be a little bit site specific, but what we found is we probably like to have a volume that's at least 5 to 10 mils, and certainly the more the better. But that's certainly also a factor in how you evaluate some of these collected data. So let's go to to slide number 43, how about some of this other data that we like to collect, not just relying on the lysimeter data? We do like to perform some of these batch slurry tests to really help us understand the soil water partitioning, that KD, that desorption isotherm. Predicting KI, that's the affinity that PFAS is to the air-water interface. There's a lot of empirical correlations in the literature for that are actually pretty easy to apply if you know even the pore water ionic strength and your approximate PFAS concentration. Air-water interfacial area, there's again some pretty simple correlations developed by Mark Brousseau and others that if you know your grain size, you know your moisture content, you can estimate that. And you put all of that together, and that allows you, that gives you the information to estimate what the PFAS pore water concentration is based on what you measure in a soil sample. Some other things we like to monitor is soil moisture content. I know they're maybe a little pricey, but even if you just have one of them in your source area, that can at least give you a semi-quantitative estimate of what your moisture content is doing between sampling events. As Chuck pointed out, recharge estimates I think are very important, and then having some other measure, maybe using these microlysimeters, some other data to complement what you're measuring in the field, just to give you some assurance that what you're measuring in the field is a representative sample. So going to slide 44, here's an example where we use this exact approach at a DoD site where AFFF testing was performed. This is for PFOS. We have the field collected PFOS concentrations, and they're in nanograms per liter. We then applied based on the soil concentration. We did the desorption testing. We knew we had an estimate of the air-water interface, and we applied our model. And that's what you see that red bar is. And you see it's very much overestimated because in that version of the model, we didn't include absorption to the air-water interface. But when we include that in the model, we can see we get, I think, fairly reasonable agreement with what we have, what we measured in the pore water. And I think that really points to the utility of these types of measurements and gives us a lot more confidence in our lysimeter data as well. So let's move to slide number 45. And one thing we haven't talked about too much is background PFAS concentrations. And maybe Chuck, maybe you'd like to talk about this a little bit.
Yeah, so some of the Navy PFAS experts asked us to put this in there. This is becoming more of a big deal at our PFAS sites. So PFAS background assessments, they're going to be a component of remedial decision-making at DoD facilities. Here's this memo, so just wanted to show that to you. Let's just do two quick slides. Here's a profile on slide 46, just talking about all these potential different sources you have to look at. Many of us, I think, have heard that it can be in the rain in some places. So taking a precipitation sample, may be important, but maybe you're also, in terms of leaching, as you're also looking at, any sort of point sources of PFAS, atmospheric industrial releases that went up into the air up in there. So the background's got to think about, are there point sources that are contributing to our sites that we're looking at, and what are the non-point sources? And then slide 47, it's got that 46 was a profile. Here's a plan view. You're looking down. Here's a stream. Here's that AFFF source area and the plume in the middle. It talks about you're going to put some of these things around there, and you're going to put a precipitation sampling location, in there to see what nanogram per liter is showing up in the rainfall. And there's some of these pore water suction lysimeters that Charles, talked about in that sort of that light gray, that true background area. And then this talking about going into the stream, you're going to do an upstream and a downstream. Okay, well, let's go to slide 48. Now, just a little bit about the models. And again, this is for you who think about, you like the math, you like these transport equations. And we're going to talk about a hierarchy from going to simple to complex. But one of your themes, Charles, is you think these simple models, like you're going to talk about on slide 49, can be pretty useful for us trying to figure out how our sites are working, right? So what's going on slide 49?
Yeah, that's right, Chuck. And sometimes a simple model is sufficient. If you have, these KD terms, these KI terms, know the absorption to the air, desorption from the soil, absorption to the air-water interface, you can essentially do a simple, Excel spreadsheet type model. And what we found based on both field and bench scale data is that we can get a pretty decent prediction of the PFAS mass discharge and also source longevity from applying these types of models. So if we're careful and collect the right data, really no need for a more complex model in some cases. And on Site 50, that's exactly what we did. We had a test cell in an AFFF area, and we did some enhanced irrigation there to basically give us roughly 20 years of rainfall. And of course, when we stopped that, we got some rebound. But then we just applied those mass balance, soil desorption KDs and KI models, and those red dashed lines kind of predict where we would expect to see things re-equilibrate, and it's pretty much spot on. Of course, there are some fairly large error bars in the field data, but it certainly seems like a reasonable prediction. And I think not only proves this type of screening level modeling is useful, but also demonstrates how important collecting the right bench scale leaching data is. Now, Chuck, why don't you talk a little bit about some of the other modeling approaches on slide 51?
So this is again from this great University of Arizona research team. This is from BOGO. Mark Brousseau certainly played a big role in sort of the underlying physics of these things, but they're developing this trio of models. Tier 3 is more of a simple spreadsheet, sort of constant flow, things of this nature. Hydrous is in the middle. This is an adaptation of that to account for that air-water stickiness for the long chain PFAS. And then they've got the big dog, this guy that, when they start running it, the lights in Arizona start to dim a little bit just because of the energy it takes. But there's this area of model complexity on the x-axis and this computational parameters on the y-axis. And this is the screening one's about to come out. I just checked this right now, and you can do a search for ESTCP, PFAS Leach, and get to that project webpage, and pretty soon there's going to be a place you can download this. And I think unofficially, Dr. Go is distributing it to people. Let's go to 52, and this is using one of the very complicated model I talked about before, and just again to show you this revenge of the geologists, this heterogeneity. On the bottom, they're running this model, and after a certain period of time, you just see after 80 years, this thing's slowly sort of moving down on this nice uniform thing. But in real life, you mix in a little bit of heterogeneity, a little bit of silt, a little bit of a pinch of silt, a little bit of clay, and you get this stuff in pockets. So pretty interesting paper about the heterogeneity. In slide 53, this is coming from Australia, Dr. Ilka Wallace, just a really nice, elegant paper. And here is this modeling from 1970 to the year 2070. X-axis is this total PFAS pore water concentration of that cross-section you see there. And you can see they've got these three big pieces. One was, yes, evapotranspiration, but they didn't turn on that air-water partitioning. Number two, yes, evapotranspiration and air-water partitioning. That's sort of that light gray one's the most accurate one. But if they turned off this evapotranspiration piece, this was a semi-arid site where that soil dries up and that pore water sometimes is moving upwards. It just says this whole thing cleans up super fast. So this knowing all these processes are important. So let's wrap up with slide 54, and then we'll go on to 55. And I'm just repeating that one before. Some of our key themes is you got to get the grams per year pore water concentration times recharge times some sort of area. And then Charles, how do you get these PFAS pore water concentration? What's your recommended approach?
Yeah, my recommended approach is really a multi-tool approach. I think we take advantage of the field-based porous cup suction lysimeters, but then you also use some of these bench scale leaching methods or bench scale pore water sampling methods. And how about the recharge, Chuck?
Yeah, and so the recharge is, so we're talking about these different methods. Some are better for humid, some for arid. That paper can sort of align you to which ones you can do on a desktop and which one, a little bit of field data, you get a lot more accurate. Then dilution factor, where you compare that vertical leaching to horizontal groundwater flow, that's a key equation. And if you want to do models, we talked about that. It's yes, if you want to try to get some understanding of what might happen in the future, but you don't have to use a supernumerical one. There are these different tiers of model, and apply the tier to the one you want. Charles, anything else you want to wrap up before we end?
Yeah, well, just with the models, Chuck, I would just say that, sometimes, the model you use might, at least in part, be driven by your geology, right? If you have complex geology, that might point you to a more complex model, right? So that's also a factor in your model selection.
Cool. Yeah, that makes sense. And I think that's it for us.
Thank you, Chuck and Charles.
Slide 56, right? Yeah. Mm-hmm.
Yes. So we have been collecting all of the questions submitted throughout the presentation. If you have any additional questions, please make sure to submit those now. So I'm just going to read some of the questions that we've received. So the first question we have, on slide 40, you mentioned multi-level lysimeters. Could you provide more detail about the thinking and strategies regarding the vertical placement of suction lysimeters at a site?
Yeah, I'll chime in a little bit on that one. Part of it is, if you recall the slide that we were looking at, the soil concentrations, right? So if you put your lysimeter beyond where it looks like any PFAS is migrated, and compared to a shallower location where you see PFAS, you're going to have two different interpretations and two different sets of data for your pore water. So depending on what the concern is and what you're trying to model, that might be an instance where you consider multi-level lysimeters. Also, if you have some fine grain materials, some silty sands, clayey sands, things like that, versus a more sandy material, that might also, at least for some locations, might point you in the direction for using multi-level lysimeters. Chuck, you have any thoughts on that?
Well, just stepping back, and we've got some sites where we've monitored and put sensors in the shallow and the deep, and there's all this stuff that goes on in that first meter. Sometimes a meter and a half. The soil is getting wet, it dries out, and there's a sort of developing thought is you want to go deep maybe, and in some ways trying to get a deep sample where there's all this stuff's been sort of muted out. And that's the stuff that's getting close to the groundwater. Get below that zero floodplain. It could reduce a lot of the noise, I think, of this. Still speculative, but I'm thinking for these lysimeters, maybe the sweet spot is trying to get down deep.
Yep.
Okay, thank you. So the next question that we have, when is it best to sample lysimeters? During dry periods, wet periods, in between, seasonally?
Yeah, so I think it makes the most sense in general to try to sample after there's been some sort of rainfall event, right? That's when there's the most water recharge, and those are probably controlling when you see the most mass discharge to groundwater. So within a day or so of rainfall, and that's when it's really nice to also have some of those moisture probes in the ground, because you can see when that slug of water is moving down. I think it becomes much more important to time it that way when you're at a semi-arid or an arid site, because in those cases, you may not even be able to get a pore water sample unless you kind of coordinate it with some sort of rainfall event.
Yeah, I'll just echo that. Is that we were doing some of this sensor work in the Vado zone at a wet site and a dry site. And this dry site, yeah, it's hard to get that water out. So we're looking at our soil moistures and our matrix potential potentiometers to see when it looks like that water is flowing, and then we'll send our team out to try to snag a sample. We're also asking ourselves, do you need those, or can you just sort of watch the rainfall and even maybe watch the radar, and maybe that's enough? So these are some things we're going to try to put into our ESTCP report in the end about some of those strategies.
Okay, next question. How does pore water contribute to the understanding of PFAS background?
Well, I'll start out is that you know, in our chart that we showed, I think it was on slide 47, there was a suction lysimeter, a couple of them in the gray zones. And I think this is just trying to see if you do have something, it'd probably be in the precipitation. And does that show up there? Or maybe historically there was something that happened out there. Maybe historically, did anybody use biosolids? So they can be a part of this background assessment to try to you know, figure that out. And then it just depends on what concentrations you see there, you know, versus trying to distinguish or what's happened, how much of this is coming from the AFFF. And usually the AFFF sites, the concentrations at many of these sites are so high, the background's not going to matter that much. It's really just on that fringes. Now, Charles, do you agree with that, or am I exaggerating sort of this importance of saying?
No, I think you're I think you're on point, Chuck. You know, one thing we've found, and this is for some work in some non-AFFF impacted areas, and getting some background samples from some supposedly pristine sites. You know, we do see, you know, tens to maybe even hundreds of nanograms per liter of some, at least in shallow pore water within a few feet of the surface, some of these short chain perfluorinated carboxylates. So I think, you know, I think there's still a lot to be learned, at least understanding the total organic fluorine load with respect to PFAS in pore water. But I would think most of the background levels are probably more limited to your shorter chain PFAS. And even then, they're still orders of magnitude less than what you would find in AFFF impacted source area.
Yeah, probably still needs to do it because these current MCLs are just so low that there is these cases when this could be a big factor. And that's why the DoD says, yep, go out there and do that background study. Mm-hmm.
Yep.
Okay, next question. Did you see that the field lysimeter data correlated better to the soil core pore water data at a certain moisture content?
So where we've done those tests, you know, they were at multiple, multiple moisture contents, and for some of the bench scale work, we actually wetted the soil a little bit to get the pore water sample, but we could account for those differences knowing the moisture content. So I guess that's the bottom line answer to that question is it seems to work for a range of moisture contents as long as it's wet enough to get a pore water sample.
And I'll just add some of our data. There is quite a bit of variability, you know, in the suction lysimeter data, you know, over time, but that's just the nature of the beast. I think with almost any environmental data, it's a very dynamic system, and you do see some of that variability. So you get, you know, some variability between sampling, you know, time A versus time B versus time C.
All right, thank you. So thank you for all of you who submitted questions, and thank you so much to our presenters for your thoughtful answers. And for sharing your experience in PFAS leaching. If you submitted a question that we were not able to get to, you can reach out to Jovan Popovic or myself directly at the email addresses shown on this slide here. Next slide, please. As we wrap up, please make sure to take this survey that will be emailed to you when you leave the webinar. Again, the survey should take less than 2 minutes to complete, and it provides us with a lot of valuable feedback on the webinar. Stay tuned for our next OER2s through the T2 email. If you are not receiving our T2 emails already, you can put a message in the chat box asking to be added to that list. We also post the OER2 presentations and recordings to the ERB website as well as the YouTube page, so make sure you check out these pages. Thank you all again for attending this OER2 webinar, and we look forward to having you back the next time.